this video, we're going to look at solving a linear programming problem. So let's consider this equation that I wrote up here, z equals 2x plus 5y. So with particular linear programming problems, you're always trying to maximize or minimize what we call an objective function. So we have that this equation that we have right here is called an objective function. And typically, yes, we're trying to maximize this equation. Now, we're subject to some constraints, of which we have x plus 2y is less than 6, negative x plus 2y is less than 2, x plus y is greater than 1, with the conditions that x and y are non-negative. So what that does is it tells me that I'm restricted to quadrant 1. Now, what we can do here is find the feasible region. Now, we can find the feasible region respectively by looking for, say for example, the the inequalities and where they fall. So we have 1, we have 2, and then we have 3 that we have to look at. Now, we'll do this in a way of which that it requires not too much work. So let's just go ahead and have this right here. So what I'm going to do is I'm going to look at my inequality 1. Now inequality 1, I know basically that the x-intercept is given by the following. It's given by 6 comma 0, and then we have that the y-intercept is given by 0 comma 3. Now if I look at the second inequality, similarly, I have that the x-intercept is going to be negative 2 comma 0, and then we have that the y-intercept is going to be 0 comma 1. Now I also have that the third inequality, if I look for the x-intercept and the y-intercept, it's going to be 1 comma 0, and the y-intercept is going to be 0 comma 1. Now if you're having trouble finding, say for example, the x-intercepts and y-intercepts, remember that in a previous video I mentioned that if you have a boundary line of the form ax plus by is equal to c, the x-intercept was given by c divided by a comma 0, and the y-intercept was given by c divided by b. So you can use this formula if you want to. The only reason that we do it this way is just because of the fact that you have multiple inequalities that you have to deal with. So let's go ahead and graph each of these boundary lines using the given information. So we'll try to make this somewhat to scale. Okay, so we have, let's do it like this. Okay, so let's do 0, 1. So there's 1. And let's see, okay, we'll make 1 right there. So we know that we have 2 points right here. So we have 0, 1 and 1, 0. Okay, but all that I need to do there is to form that line that passes through both of them. So we have that there's going to be a boundary line right there. Now I also need to graph negative 2 comma 0 and 0 comma 1. But notice that when we graph this equation, basically we're going to find that the line has to go from here to here. But notice that basically it's not going to matter where that line passes through technically. I'm sorry. What I mean to say is, like, it doesn't matter that it passes through here because of the fact that it's not within the boundary or within the feasible region. So all that we have to do is just kind of like draw an imaginary line. But if you want to, you can also just plot another point so that way you know like where did it pass through. Okay, so this is the second one. So the equation that corresponded to the second inequality was negative x plus 2y uh, is less than or equal to 2. So what that means is that if I plug in 2, I should get also 2. So I'm just going to do it like this. We have 2, 2, and then we have that the line is going to go something like this. Okay, now I need to get the other point, which in this case is 0, comma 3. So we have 0, comma 3. Okay, so we'll put 3 right there. And then we have 6. Okay, so let's see. Let's do it like this. Okay, so this right here is going to be 6. Now, we have that essentially this point of intersection right here, it happens to be at the ordered pair 2, comma 2. And then we have that there is also a point of intersection right there at 0, comma 1. And then we have this ordered pair right here, 1, comma 0. And then over here we have 6, comma 0. Now we do have 0, comma 3, but I'm not going to notate it because there's a specific reason why. So looking back over here, we have that each of these inequalities, the first one and the second one, they're both less than or equal to and they're positive. So that means that the shaded region is actually going to be below. So we also have that this one is going to be below. But over here you have that it's greater than, which means that it's going to be above. So we have to go back and we have to basically just notate that the shaded region has to be below both of these two lines, but it has to be above this one. So what that does is it basically gives you this region. Now, I have that the feasible region that falls over here, it's basically what we call bounded. So we have that this area is bounded, but we also have that there are a set of corner points. So we have that the corner points are as follows: 0, comma 1, 2, comma 2. We have 6, comma 0, and then we have 1, comma 0. Now, typically when it comes to these types of problems, we're actually trying to optimize or maximize or minimize. So let's say that we were to make like a table of corner points. And let's say that we call this the objective value. Okay, so we have a set of corner points. We have that there's going to be a corresponding objective value. Now, we'll do this in the following manner. We have 0, comma 1. We have 2, comma 2. We have 6, comma 0. And then we have that last one that I can't see is 1, comma 0. So we have 1, comma 0. Now we're plugging this back into the objective function that is z. So recall that that was z equals to 2x plus 5y. And you can go back up here and see that basically the objective function was 2x plus 5y. Now the thing of which that we need to do here is just figure out like which is the largest or smallest value that we have. So we have that basically for 0, comma 1, that's going to be z equals to 2 times 0 plus 5 times 1, which is equal to 5. Similarly, we do the same thing for 2 times 2 plus 5 times 2, which is equal to 12. We do the same thing and we find that z is equal to 2 times 6 plus 5 times 0, which is equal to 12. And then finally, we have that z is going to equal to 2 times 1, and then we have plus 5 times 0, which is equal to 2. Now, as I kind of go through both of these, I notice that basically there is 2 points of which gives us a maximum value. But then I notice that there's only one that gives me a minimum value. Now, it is possible to have 2 of each, or multiples. So notice that with here, we had that there was a maximum value of 12 from at the points 2, 2, and 6, comma 0. This means that basically that there's going to be a maximum from the point 2, 2 all the way down to 6, comma 0, meaning that we can choose any more points along this line, and there's a way to phrase it nicely. So we have that there's a minimum value of 2 at the ordered pair 1, comma 0, and then you have that there's a maximum value of 12 at 2, comma 2, and let's say like this. There's a minimum value of 12 at 2, comma 2, and every point in between, we said 6, comma 0. I mean, we could say, maximum value of 12 at 2, comma 2, and 6, comma 0, and every point in between. We can say it like that if you want. It's the same thing though, as long as you kind of understand that the maximum has to be alongside here. So with that, like if x was equal to 3, then in that case, you would have 1/2. You would have 1/2 as the x value, but then you would have to figure out like what is the y value then. Well, if you put 3, then yeah, 3, comma 1/2. Sorry. Yeah, 3, comma 3/2. Okay, and then similarly, like if you did 4, then you would have that this is going to be 4, comma 1. So 4, comma 1 is also a maximum of the same thing, 12. When you get into more questions that ask about maximums and minimums, it's going to be very specific. Okay, so just be sure that you look at the different examples in the chapter. Basically, you're always going to have that the question will either say maximize or minimize an objective function that is usually of the form ax plus by, and then you have that it's subject to the constraints and the constraints typically depend on the scenario. So actually, it could be of the form like ax plus by is less than or equal to c, or ax plus by is greater than or equal to C. But then most of the time you have that the last constraints uh, is that X and Y are both strictly positive. So be sure that you do look at those different examples where you have that you're restricted to the first quadrant and then you're using maximize or minimize.